Today's lesson is on entropy, and we have moved on to chapter 16, still under the thermodynamics unit, but a separate section to that unit and a new chapter. So our text reference for this part of the unit will be chapter 16. So I want to start by saying that probably right now your bedroom has a very high entropy. You probably don't understand why I'm saying that, but by the end of this lesson, you will understand why I made that statement about your bedroom. In the previous lessons on thermodynamics, we explored the first law of thermodynamics, and that first law is just used as energy bookkeeping, and I have a few bullet points there. We talked about how much energy is involved in a change. Does the energy flow in or out of a system? What's a system? What's the surroundings? So we used this first law to keep track of the flow of energy and the amount of energy. And was the energy heat? Was that the form? So now we're going to investigate why processes even occur, and why do they occur in specific directions. So the first thing we want to talk about is spontaneous processes or spontaneous reactions. Some reactions are spontaneous and others are not. A spontaneous reaction will occur without anything helping it along, so no outside intervention. I don't need to add energy to keep the reaction going. I don't need to add a catalyst to make the reaction happen. They happen on their own. I've put a few examples on this screen. So if we think about a ball rolling down a hill, I don't need to continuously push the ball to get it to roll down the hill. It will spontaneously roll down the hill, but it will not spontaneously go back up. So pushing the ball back up the hill, I have to continually apply a force to that ball. That would be non-spontaneous. If you look at example B, steel rusting, we say is spontaneous because it's going, you put your bike in the rain, it's going to spontaneously start to rust in certain areas. But it doesn't spontaneously turn back to iron metal. So once it rusts into an oxide, it's not going to turn back into that iron metal. So rusting is spontaneous, but turning it back into its reactants is non-spontaneous. And then if you look at letter C, you can see here water will spontaneously freeze at 0 degrees C, and it will spontaneously melt at temperatures above 0 degrees C. It doesn't need anything to make that process happen. If the temperature is 0 degrees C, it's going to freeze, and if the temperature rises to above 0 degrees C, it will start to melt, and it does that on its own. So we call that a spontaneous process. So just to also make something clear, in chemical reactions, these reactions might occur immediately, or they might occur over very long amounts of time, maybe even millions of years. But as long as it's occurring without outside help, the reaction is spontaneous. And one good example of that would be when we talked about carbon as a diamond. Moving or transforming into graphite. So a diamond becoming graphite takes millions of years. So it takes a very long time for this to happen, which, like I said before, is a good thing because we wouldn't want our diamond rings or our diamond earrings to spontaneously become graphite fast. So we're happy that this reaction takes a long time. But it is a spontaneous reaction. It doesn't happen very, very fast, but it does happen without outside intervention, without anything being added to the diamond for it to become graphite. So that's just a good example of something that takes a long time, but still spontaneous. So why do spontaneous reactions occur? Well, let's look into something called entropy. So entropy is just a measure of disorder, and it has the symbol S. So capital S stands for entropy, which you can see I have written right here after the word entropy. So that's the symbol that we use. Anytime you see S, it stands for entropy, just like we used H to stand for enthalpy. So entropy, again, measure of disorder, and spontaneous reactions increase entropy, or they increase the disorder of the universe. So having a spontaneous reaction means that we have high entropy. So this brings me to my bedroom example that I mentioned earlier. When you clean your room and everything is in order, in its place, you have very low entropy. Everything is in its specific position. But it certainly doesn't take long for your room to get disordered or messy. And so your room has very high entropy once things get out of place. It's not easy to keep your room clean. It takes a lot of outside intervention. It takes you putting things back in its place in order to keep that low entropy, in order to keep it clean. So your bedroom easily, spontaneously becomes disordered. So that's why I say your bedroom has high entropy. Let's take a look at a deck of cards. On the left, you can see that the cards are all organized. They're ordered by their number, or if they're king, queens, aces, jacks, so on and so forth. If I took those cards, and if we were in class, I would actually do this. This is one of my demos. And I kind of just threw the cards up in the air, dropped them on the floor. Would it be likely for me to pick up those cards in that same ordered way? I went from a very ordered way, low entropy, dropped them on the floor, and you can see the picture on the right. It's definitely not going to be likely that I would pick up each of those cards and I would pick them up all in the same ordered way as they were before I dropped them. So nature spontaneously proceeds to states that have highest probability of existing. And that usually means high entropy, and it usually means a lot of disorder. It's hard to keep those cards in an ordered, organized way. Once you start using them, they automatically become unorganized and have high entropy, just like with your bedroom. So nature, or the cards in this case, have billions and billions of ways to be disordered, but only one way to be ordered by their numbers. So we would say that there's low entropy on the side where they're ordered by number. So low, and I'm just going to say S. And on this side where we have lots of disorder and high probabilities of them staying disordered when I pick them up, we would have high entropy. Now let's actually look at and analyze this sample of gas. In the top picture, you can see that the valve is closed on this system. And all the gas is on one side. And we want to talk about why this process is spontaneous. Meaning, why do those gas molecules move to the other side once you open that valve? So then you see here, valve opens, and you'll see a movement of molecules spontaneously over to the other side. And it fills both chambers evenly. There's definitely many ways that the gas could fill both the chambers, meaning I could have 10 particles on one side and 100 particles on the other, or I could have all the particles on one side and none on the other. But it doesn't do that. This is the most probable way. Gas is going to flow from one side to the other, and it's going to increase the disorder of those molecules. The molecules on this side are kind of all packed together, less movement, low entropy, so low S. If I look down at this bottom picture, I'm going to say I have high entropy because the molecules now have lots of room to move around, and they'll spontaneously expand to fill that vessel evenly. And it's very improbable that gas molecules will stay on one side of the vessel, or that they'll unevenly distribute to both sides of the vessel. So that's just another look at something that you might actually see in chemistry, which is gas molecules. Now I want to move on to some examples in your textbook. So the first example we're going to look at is sample exercise 16.1. It's on page 754 in your textbook. And it's asking you which has higher positional entropy. So basically which one has more order and which one has more disorder. So here we're going to look at something that is in the solid phase. So we have CO2. And when we talk about solids, remember we have all the molecules or atoms packed together, not much movement. So we would say that solid CO2 is very ordered. Those molecules can't move around much. And there's not many choices of arrangement for those atoms. They're pretty much going to stay where they are. But then I go to gaseous CO2. And these same molecules now have a larger area to move around. And so we've created a system that has more disorder. There's lots of different arrangements of the molecules. They could be arranged the way that I have them here, but they're all moving around. So the arrangements of those molecules or atoms are going to be very different and more disorder. So there's greater entropy on this side where it's a gas, so greater S. So we can say that delta S is positive. And we'll get into a little bit in some of the other examples what delta S stands for. Now the second example, they're both gases. We have nitrogen gas. One is at 1 atm. The other gas is at 1.0 times 10 to the negative second atm. So one has higher pressure than the other. And so I want to think of these in terms of Boyle's law. So at 1 atm, we have higher pressure. That means we have a lower volume. If I have a smaller volume for these molecules to move around, that means I have less space for them to move around. If I look on the other side where I have a lower pressure, lower atm, my volume is going to be increased. So now I have more space. If I have more space, I have more area or more positions that these molecules can position themselves. So I have more disorder on this side, so delta S would be positive. I'm going to move on to sample exercise 16.2. That's on page 755 in your textbook. And here we are predicting the sign for entropy change, which is what I did on the last slide. But I also talked about how many positions you would have at a lower volume versus higher volume, or solid versus a gas. But I also put in there the sign. So here we're just going to predict sign. Is there more disorder? S will be positive. Is there less disorder? S will be negative. So that's what we're going to look at in these examples. So again, we're looking at solid sugar. So I've got a sugar cube, and I've got molecules of sugar all packed in that sugar cube, okay? And I have a glass of water. And I take that sugar cube and I add it to the water. Well, you all know that that sugar is going to dissolve. And when it dissolves in the water, you're going to have sugar molecules floating all around in there. They're not going to be tightly packed anymore into that sugar cube. They're now going to be dispersed throughout the water. So if I add sugar to water and I form a sugar solution, I'm going to have high entropy. I'm going to have molecules dispersed throughout the water, taking up lots of different positions, positional arrangements, as we said in the last slide. So here, my delta S would be positive. My delta S for just the sugar cube, if I were looking at just the sugar cube, but it's not asking me that, the delta S here would be negative because it's very ordered, less disorder, really only one way for those molecules to be arranged in that solid. All right, second example, we have iodine gas condensing, and forming crystals. So I have I2 gas, and it's forming solid iodine as a product. So here I'm going gas to solid. So here I have on this side, as a gas, I have more disorder. As soon as it forms that solid, it condenses into those solid crystals, I have less disorder. So in this system, since I have less disorder as a product, my delta S would be negative in this case. It's not thermodynamic, or it's less disorder, not thermodynamically favorable. So more disorder to less disorder, entropy decreases, so we have a negative delta S for that example. So this slide I just want to do a little bit of an overview, just kind of review the notes that we just did. Here it's saying if delta S is greater than 0, so delta S is positive, okay, which is what we were talking about in the last slide, that means I have an increase in disorder. So maybe that means I'm going from a solid to a liquid, or a solid to a gas, or a liquid to a gas, but I'm increasing the disorder in the system. Sometimes it'll mean I'm dissolving something. We talked about these two that I have circled. If I look at this temperature increase, if I increase the temperature of something, that means I'm increasing the disorder because molecules are moving faster and it's causing more disorder, more positions that those molecules can be in. And if I look at this moles of product, more moles of product than moles of reactant, if let's just say I have 2 moles of reactant and I'm forming 3 moles of product, and of course we're only talking about gases here, I'm going to have more disorder where I have more moles of gas. So more moles of product than reactants, I'm going to have more disorder. So that would be a delta S that would be positive as well. And we're going to look at some examples of that as well. And here I have delta S negative or less than 0. That means things have become more organized. That would be like if you cleaned your room. Now the delta S of your room is less than 0. But that is thermodynamically unfavorable. It's harder to keep things in an arranged order than it is to keep them messy. And that's why your room tends to get a lot messier. Okay, so hopefully that gives you a really nice little review of entropy. I have one more example that I want to talk about on the next slide, and then we'll be done with this lesson. Now I moved ahead a little bit in the book. I'm not doing this chapter in complete order, so I moved ahead to page 763 for this sample exercise, but here we want to predict the sign of delta S based on the reaction that's occurring. So we want to look at what's happening in the reaction. What are my states of matter? How many moles of gas do I have if I'm dealing with gases? So that we can predict those signs for delta S. So in the first one, I started with a solid calcium carbonate, and it produces CO2 gas, so I have some gas formation, and it also forms calcium oxide solid. So I took a solid and it formed a solid and a gas. So if I look at this ordered calcium carbonate, because it's all solid, and I'm going to something that's less, let me fix that word, I want to write disordered. It's disordered because I have that gas formation. Gases tend to be disordered. So if I'm going from a solid and something forms into a solid and a gas, I've made it messier. I've made those molecules have more positions that they could be in. So entropy increases. So my delta S is going to be positive. I've created more disorder in this reaction because of that gas formation. Okay? So let's look at the second example. Now the second example, if you take notice of the states of matter, and that's where I always go to first, let me see what physical states I have. I have a gas and a gas on the reactant side, and I have a gas on the product side. So on the reactant side, I have 2 moles and 1 mole here of gas for a total of 3 moles of gas. On the product side, I have 2 moles of gas, so I'm going 3 moles to 2 moles. And if you remember on the last slide, we said if I increase the number of moles going from reactant to product, entropy increases. But in this case, I'm going from disorder to more ordered because I'm only having 2 moles of gas. So entropy is decreasing on the product side. So here I would have a delta S. I would predict that to be negative. Now I recommend that you go back and read some of the information in the textbook just to kind of help put all of this together. The next slide we're going to look at is your assignment, so I'm going to move on to that. And so I put the text reference, the pages that I covered in this particular PowerPoint, and then your homework right underneath that is from the textbook, and you're going to be looking at some problems at the end of the chapter, page 783, 23, 24, 33, 35. Again, you can do this in Notability, take a picture of it, or send it to me as a PDF. You can do it on loose leaf, send me a picture or PDF, but please make sure you're handwriting your assignment. And this is due on Tuesday, April 21st in the Dropbox. I hope this was helpful. Also, I'll be putting some videos up just for you to kind of look through in this chapter to maybe reinforce some of the things that we're going to be talking about as far as entropy and Gibbs free energy and how it all relates to enthalpy. So we'll be talking about all 3 things in this chapter. Have a great day, guys, and I will see you later for our next lesson.